Now guys, put the heading Demodulation of FM Signal. Guys, we need to understand you're asking, can we pass AM wave through frequency multiplier? Yeah, you can do that. Yeah, you can put an AM wave of mu less than 1 and it can give you narrowband FM to wideband FM. But one thing that we should know, that if you take an amplitude modulation, there is a phase shift of the lower sideband. If you recall, in AM and narrowband FM, the only difference is a phase shift. So that will create some distortion, right? So it's not advisable. Gate can ask a question like this because it's thinking on a very, it's not a like a practical question. It's more on like, can we do this and that mathematically? So mathematically, yeah, you can do it, but practically there's no point because we already have a narrowband FM. Okay, clear, or still you have any question on this? Okay. So guys, in this we have two techniques of demodulation. So, but what do you mean by demodulation of FM signal? Demodulation of FM signal is exactly like any other demodulation. Your aim is to take the FM signal and get the masses out of it, right? So your whole sole aim is to get the frequency as input and get the output as voltage variation. So if you go on this slide, there are two techniques, and the first one is known as frequency discrimination method. Frequency discrimination method. Frequency discrimination method, FDM. And in this we will study balanced slope detector. Balanced slope detector. Now guys, to make anything balanced, I will just open up this 3 keywords and you will be really happy to see the way I open it up. You will be like really impressed. Balance means there will be two set of or two units of the circuit. Slope means you will have a differentiator circuit, and generally to use a differentiator you need some filter or some tune circuit, right? That's how you create a differentiator. So you will get a tune circuit. Detector is what? Detector is the last building block, and we are using which detector, guys? It is envelope detector, which I have taught you so well that you should not forget that. Envelope detector. So now you can clearly understand how you are discriminating on the basis of frequency to get the masses signal. So you are using two tune circuit, right? And both the tune circuit are tuned at two different frequencies, one above the carrier frequency and one below the carrier frequency. There are two set of tune circuit. That's why we call it as balanced. Why we call it as slope? Because you have a differentiator circuit, because the tune circuit is like a more on like a low pass filter, and the end output, or you can say the end block, is envelope detector, because once you have got the certain masses signal, certain frequency, for a certain frequency you have got the masses signal, you need to demodulate into again the m of t, because that frequency variation you have got for that certain frequency range, still it has to be converted back into masses signal. So that's why we call it as balanced slope detector. Okay, any doubt? The other is known as phase discrimination method, and it is going to discriminate on the basis of phase, and that we'll be doing by using a PLL. PLL is, guys, what? phase locked loop. So we try to monitor or track the phase deviation and convert into message variation. So let me take one by one. So first you can write balanced slope detector. Okay. So it's just like inverse of what you have seen as VCO. So write, it is a frequency to voltage converter. That's it. VCO is voltage to frequency. It is a frequencies to voltage converter. That's it. Okay. Now, if I look at the block diagrams, you have FM signal, which is the input. Guys, by default, when I say FM signal, it is narrowband FM signal. So it is tuned circuit. Okay. The another tuned circuit. Okay. Then it goes into an envelope detector. Envelope detector. So each of the tuned circuit is followed by an envelope detector. Okay. And then you get a voltage as V1 here. You get another voltage as V2, and you put into a summer. So this is plus, this is minus. You get V1 minus V2 as the masses. Now, this is like the frequency of this FM signal is instantaneous. Continuously it is changing from one frequency to another. Basis that it will also be changing. Because V1 minus V2 is completely depend on this whole, you can say each of the block. And as frequency is changing, V1 is changing from the first part. As frequency is changing, V2 is changing from this part. So V1 minus V2 is also varying. Okay. Now we'll call it as that this is tuned circuit 1. Tuned circuit 1. This is tuned circuit 2. It is tuned at resonant frequency FR1 and it is tuned at resonant frequency FR2. Clear? We'll discuss the working principle in a while. Let me take Chetkar's question. Why narrowband FM signal? Who told you this is narrowband FM signal? I've just written FM signal and the heading is generation of wideband FM signal. So demodulation we are also doing for wideband FM signal. Going further, if somebody says FM signal, it is always wideband, not narrowband by default. Always keep in mind. Okay, so maybe there is confusion then. I might have slipped there. Generally, it is wideband FM. Don't take narrowband FM. You can think logically also. Narrowband FM doesn't have any application. So when somebody says FM signal, you should go with wideband FM. Okay. Anyway, it is wideband FM signal, guys. So no confusion now. Maybe I might have said that. I don't disagree. It can be possible. My brain is thinking something, I might sometimes slip my tongue. So, but it is wideband FM. We are very clear on this. No doubt? Okay. Now there are three cases, guys. Case first, when Fi, instantaneous frequency, is equal to Fc. So guys, this is your instantaneous frequency. Please add it, this I missed. Instantaneous frequency Fi. Now if Fi is equal to Fc, case 1. Case 2 is when Fi is greater than Fc, right? And case 3 is Fi is less than carrier frequency. These are the 3 cases. Okay? Let's start one by one, but before you go and do so, let's have the characteristics of the gain characteristic of these tuned circuit. So this is gain and this is frequency on the x-axis. Okay? So let me draw the first tuned circuit gain characteristics, and this is the other tuned circuit. Now we know that this is the resonant frequency for first tuned circuit, so call it as 1, FR1. Okay? Where they are intersecting, call it as FC, carrier frequency. And this is the resonant frequency for FR2. Okay? Now you understand, when you are at resonant frequency 1, gain of the tuned circuit 1 is dominating on the gain of the tuned circuit 2. Because here you are at the peak, but for blue graph you can see it is at a lower value. Can you see it, guys? And similarly, when you are at the tuned circuit 2 frequency FR2, then the tuned circuit 1 has a lower gain. Are we clear on this? Now, we'll go case one by one. So case 1. When instantaneous frequency is equal to Fc. Fi is equal to Fc. Now what will happen if Fi is equal to Fc, both are Fc, right? So both are going to give you same voltage. V1 and V2 will be equal. So I can write, when Fi is equal to Fc, output of envelope detectors 1 and 2 are same. Output of envelope detectors 1 and 2 are same, which implies that V1 minus V2 equal to 0, right? Means V1 equal to V2. I can also call it as that no message received. M of t equal to 0. Any problem in this case, guys? Because guys, this is coming from the gain of the tuned circuit. At Fi equal to Fc, both the gains are same. Let's call it as Fi, the x-axis is Fi. Okay? That's why gain is same. Both the gains are same of the tuned circuits. So V1 is also going to be same as V2, and when I do V1 minus V2, which is empty, it is equal to 0. Any confusion? Now we'll take case 2. What do you think, guys? What will happen in case 2 when Fi is greater than Fc? Anyone in the class? You're writing yes, no. Any question, please ask. Case 2. I'm saying when instantaneous frequency is above the carrier frequency. So when Fi is greater than Fc, means somewhere here. So I can say it is somewhere here. I think somewhere here, let's say here. Fi is somewhere here. So you can clearly see that this gain is more, so V1 is more than V2. So I can say when case 2 is there, then gain of first tuned frequency, gain of first tuned circuit is more than gain of second tuned circuit. Means what? V1 minus V2 is greater than 0, or you can also say that M of t is positive. So here you will get positive message signal. Very good, Shivam, you are right. Last case, guys, case third. Instantaneous frequencies below Fc, the gain of first tuned circuit is less than gain of second tuned, the gain of second tuned circuit. So we can call it as V1 minus V2 is less than 0, negative. So message will be negative. See? And you can clearly see it from here. So suppose gain of second tuned circuit is more. So let's put a dot there. You can clearly see that gain of second tuned circuit is more than the gain of first tuned circuit. So MT is positive, negative or 0. Depends on how the instantaneous frequency is doing on the on these two tuned circuit. Why we call it as balanced slope detector? I already told you that it has two tuned circuit and they are their slopes are equal and opposite. Okay. So you can write that statement, guys. So guys, why do we call it as balanced slope detector? It's simple. Because one is giving you V1 and the other is giving you minus V2. So if I say V1 is positive slope, so the output because of the second part, the bottom part, is just negative and equal. And that's how it is known as balanced slope detector. It has two component, both are having equal and opposite slope. So write that as a note. If somebody asks you, you should be able to answer this. Right? The slopes of the two curves, must be equal and opposite. I'm talking about the gain characteristics. Must be equal and opposite. Hence, it is called balanced slope detector. Yes or no? Now guys, I am going to give you the circuit diagram for this. So we have our transformer here, see? Okay, and tuned circuit means you will have capacitor, dividing into two parts, and after that you should have an envelope detector, so you will have a diode, and then you have another capacitor like that, discharging thing, and one resistor in both of them. See, here you will be measuring V1 and here will be you are measuring V2. These two are tuned circuit capacitors, it will be variable one. This part is envelope detector, guys. See, look at the beauty of the diagram. See, what I just mentioned in English, I am able to show you exactly. So this part is your envelope detector. And this is the part you are getting as, you can say as differentiator circuit or slope. Can you see it, guys? Differentiator, you write in full, and then input is FM signal. Now how the circuit operation will work, if it is positive, so this will be like negative, so this is like going like this, so this will be going like this, and that's why it is opposite in polarity, so you get V1 minus V2. If you think this side as positive, so this will be negative, and that's why you get V1 minus V2. So this is the hardware implementation of balanced slope detector. Now this is the best we can discuss. So when I say the slopes of the two curves, this is coming from tuned frequency circuits. This is the tuned circuit ka slope. Now we are almost at the end of the FM. Then it will not be what I have drawn. I drew a very simple slope so that you can understand. But if you ask me how it should look like, it will be something like this. So you can clearly see that one has positive slopes, the other is negative slope. That's how the real tuned circuit slope look like. But why did I put both of them like this? So that it looks easy to understand. Clear? Otherwise you'll get crazy looking at this curve. Okay, now the next part is FM demodulation using PLL, phase lock loop. So guys, that is under the category of phase discrimination. Okay, that is also good. Just have a look. Put the heading. FM demodulation using phase locked loop, PLL. Let me write full form. Phase locked loop. Another analog integrated circuit. See, such a beautiful concept and subject is a communication system. They are using different subject in totality. So, guys, this FM demodulation using PLL is more or less similar as what we did in synchronous detector. I will show you. Let me have the block diagram ready. So you have a FM signal. Again, guys, it is wideband FM signal as the input. It goes into a mixer. Okay. Then it goes into a low pass filter. Right. And actually, phase lock loop is a negative feedback circuit. Negative feedback circuit. Write somewhere, negative feedback circuit. So this is VCO is going as into the feedback. Negative feedback circuit. So what will happen? Why I'm doing this plus and minus, doesn't matter, it's not an adder. So guys, let's say we call it as first order PLL. That's I'm assuming that it is a first order phase lock loop. So the feedback is of VCO itself, voltage controlled oscillator. Why and all will answer, just give me a minute. What I do, I am going to do a comparison. You have a mixer or multiplier, you get a any AM signal here as the input, you give a local oscillator carrier, okay, then it goes into a low pass filter, and then you get the massive signal, correct? This is your what detector, guys? Synchronous detector. If you recall, I have taught you in full detail. This is synchronous detector. Yes or no, guys? So if you compare this with this, what is the only difference? You see that the output of low pass filter is getting into a VCO and constantly. So what will happen the moment you give this massive signal, because anyway this is the output is empty here as well, and both are a little bit of equivalent. That's what I'm trying to make a point here, equivalent. But what I'm trying to say, the moment it goes into the feedback, you again get the FM signal, right? At the instantly you are comparing the phase, right? Instantly you are comparing the phase, and then again it goes into a low pass filter and you get the output. But that is a very raw idea or intuition that it is similar what you have seen here. The only difference that why it is getting into the feedback, because so that you can compare the phase of the FM signal at that instant, right, with the FM you are getting from this VCO. And then you can see that, okay, this is my real message signal coming out of this FM signal. Right? Any question? And now why are we doing that? Because in synchronous detector, here the frequency is fixed, which is we have assumed that here we are going to generate FC. But here, what is the problem? The problem is that here FM signal, right, the frequency is constantly changing. So you have to give the same frequency to the mixer to generate the message signal. That is very important point. You need to understand. Suppose you have a frequency here, FC, right? This AM signal having a frequency anything like FC plus FN, FC minus FN, and FC. These are the frequencies you get. Correct, guys? Yes or no? Listen to me very carefully. The whole idea you need to understand. So you get a upper sideband, you get a lower sideband, you get a carrier frequency, but all are around FC. Yes or no? That's why multiply with a carrier which is also having same frequency cos 2 pi FCT. Here frequency is fixed, which is not changing, but what is the problem with the FM signal to get the masses out of FM signal, that every instant the frequency of the signal is changing. So to demodulate, you need to shift that to a low pass frequency range, right, or low pass filter range. Then you will get the demodulated message signal, right or not? So what you are doing, you are taking the FM signal, right, and whatever the message you got after one processing, you are taking back again in the real time. You are comparing, right? You are actually mixing with the output of VCO, which will be giving the same frequency of the message signal which you want, so that it can shift at the low frequency region, and you can use another again low pass filter to get the message signal. After another instant, let's say at t equal to 1, you got this. At t2, you will get another frequency. Then another frequency will get you the another message signal, right? And you will compare with it the just before that T1, T2, before that T2 to T1, and you will see that, okay, I can shift it back to the low pass filter. This is a little tricky, I understand. Why there is a feedback? Here, why we don't have a feedback? We don't have a feedback because here frequency is constant. Here frequency is varying all the time. So in the real time, we also have to get a, mixer has the same frequency what you are getting, right? Here we were getting the same frequency because it is fixed. FC is fixed here, and you are getting FC plus FM. But this part is not as it is here, right? Here frequency is changing all the time. You really want to mix that frequency, right? Suppose here the frequency is FC1, you have to mix it with FC1. Suppose frequency change from FC1 to FC2, you have to again bring FC2 and mix it. Mixer cannot be having the constant frequency. You understand? And why do we mix it? Because you can shift in the left, in the right and the left, so that you can use a low pass filter to get the message signal. I hope I explained in full detail. Let me know did you get or not. Now whatever we have understood, we'll write. Chalo. So let me. So couple of key points. So suppose you got the message signal here, AC cos, sorry, not massive signal, frequency signal. But I think that is not required because we are not going to, exactly go into the derivation part. So just write the point which we have discussed, that the working principle of phase locked loop is same as synchronous detector. In AM, the carrier frequency is constant, FC is constant. FC is carrier frequency, guys, we know it. In AM, the carrier frequency is constant. So, local oscillator is used to generate the same carrier, but next point, but in FM frequency modulation, the carrier frequency is changing. The carrier frequency is varied according to message signal, using VCO. So, local oscillator is itself replaced with VCO. That is exactly we have done. Is replaced with VCO. Clear? I want to give an example. For example, how does, it's an intuition, so how does it give you empty? Okay? So let's say if input to PLL is this cos 2 pi FCT plus phi. See guys, I have not taken a standard FM signal, I've just taken something. So output voltage is directly proportional to d by dt of phase phi, because what is the full form of PLL? It is phase locked loop, so it is directly proportional to the phase. Clear? Now what you can do, if you think of, so this is for this, this is only for this. Now, if you think this as a FM signal, so P output T will be differentiation of d by dt of the whole phase, which is 2 pi kf integral mt dt. Recall that? Guys, FM signal format, AC cos 2 pi FCT plus beta sin 2 pi FMT when we are putting the message signal, right? Integration. But the basic is what? The very first equation I wrote. It was AC cos 2 pi FCT plus 2 pi kf integral mt dt only. So that is your phase, right? That is your phase. Because 2 pi FCT component is your carrier. Okay? So you only take the phase shift. And the overall thing, 2 pi FCT plus this term is known as angle of the cos. So if you differentiate this, and I am going to put this proportionality constant as 1 by kV, that is my intention to do it. Integrate, differentiate, so you will get 2 pi kf mt. Right? So I can quickly write V output is, this is anyway constant, 2 pi kf by kV times mt. See, you are getting your message signal. Look at the beauty. You can also think that I can write this whole thing as 2 pi kf, so this will cancel each other. That is anyway constant, you can always handle. But did you guys get the whole idea and beauty of PLL, or whether it is Armstrong method or balanced slope detector or direct method? Everybody understood generation and demodulation of FM clearly? Because that is little difficult part. Any teacher will teach you very well in modulation and demodulation, but FM is little tricky.